Test, test. Not too much is up with me. Just about ready to rock and roll here. Thanks for tuning in. Thanks for watching. Are you ready to rock and roll? Well, I got some new smart bulbs. So we're going to try to change the color real quick. Color mode. Blue, a little bit of purple, a bit of orange maybe. Kind of like the blue. You like a blue? Honestly, I don't mind the red. Boom. Alright, just about ready here. Opening up the notes on the iPad. Boom. There we go. Okay. Welcome. Anyone else live out there watching? We got any more live viewers, geometry? No? Well, what color should we start with? About purple. All right, here we are. It's and right about here is where we'll start the geometry notes. Welcome. It's September 30th. Promptly at 2:00 p.m. We're doing the 3.2 notes. Let's jump right into it. The last lesson was about reflections, and it was our introduction to transformations. Transformations, again, are these things that manipulate a figure, whether that's rotating it, whether that's flipping it, whether that's just moving it around. The one that we introduced before was reflection. Well, today's transformation is called translating. It's called a translation. Okay? That's what we're looking at today. And to help us understand translations, we need to talk a little bit about vectors and introduce this idea of what a vector is. So let's take a look at that. A vector is a quantity that has both direction and magnitude. The initial point of a vector is the starting point, and the terminal point of a vector is the ending point. So let's diagnose this right here. A vector is a quantity that has both direction and magnitude. So direction, sort of like array. So what does this picture remind you of? It reminds you of a ray. It's starting here and going all the way out here. But the thing is where a ray is infinite, a vector has a beginning and end. So that's more like a segment, right? So a vector is sort of like a ray and segment combined. Okay? It's kind of like marrying the two together. So a vector is like a segment and a ray combined. It has a starting point and it goes off in a direction, but the fact is it actually ends, which is where the segment idea comes in. So it has a direction, and magnitude is a fancy word for distance. Magnitude is just a fancy word for distance or length. Okay? So when we look at this thing over here, what can we potentially name it? We could name it EF or vector V. And notice I'm not doing like an entire arrow. I'm doing like half an arrow. Okay? I'm doing like half an arrow. And that's how we write a vector on the page, is with like a half arrow thing. Okay? So a vector can also be named using something called component form. And that's what this is right here. So this, when I write something in this form, it kind of tells me the directions, right? Think of a vector as directions. I don't really have a lot of room to write that, but think of vectors as directions, okay? It's directions on how to get somewhere. You're going to go up this much, right this much, left this much, down this much, right and down, up and down, left and up, left and down, whatever the combination is, it's directions on how to get somewhere. So the H represents the vertical change. Sorry, misspoke. Represents the horizontal movement or change. And K represents the vertical change. So this vector over here, PQ, can be described as 5, 3. And these directions tell us to move right 5, up 3, which is exactly what this vector is doing. Okay? And one other way, not to bombard you with multiple ways of listing it, but just to get you familiar with all of them, is using coordinate form. There's an E on the end of coordinate. Coordinate form. And similarly, instead of doing a super shorthand HK, instead of doing that, we're saying, okay, add H to move it to the right, or subtract H to move it to the left, right? If you add, you're going to move to the right. If you subtract, you're going to move to the left. And that Y value, if you add, you're going to move up. If you subtract, you're going to move down. So it's just another way of thinking about it. But again, vectors are directions. So let's take a look at a few of these vectors. Initial point is the start. That's pretty obvious. That's point M. Terminal point is the end. That's point N. And we could name this vector Mn. I don't think I need to dwell on that, right? We name vectors like the exact same way we name lines and rays, and we've seen that for a little bit. So this is the start, and this is the end. So to get what are the directions? Tell me what are the directions to get from M to N? We're moving 1, 2, 3, 4 to the right and down 2, right? Let's switch up the color and down 2. So the horizontal change is 4 and the negative change is down 2, so negative 2. So we would write the component form like this. And again, I'm just thinking of I'm thinking of vectors as directions. When I look at that thing Mn, what's it doing? How's it traveling? It's going from M to N, right 4, down 2. And in coordinate form, what would this look like? Well, how is M traveling to N, right? This is a coordinate right here. You realize that, right? Like if this is the coordinate plane, this would be at 2, 1, 2, 3, 4. M is at 2, 4. And if you add 4 to that and subtract 2 from that, you're going to end up at N, which is 6, 2. Right? 1, 2, 3, 4, 5, 6, up 2. So that's what this coordinate form is going like, oh, how can I get from one point to the other? I'm adding 4 to travel to N and subtracting 2 to get to N. And that's what this coordinate form is trying to show off here. So I added 4 and subtracted 2. Okay? I said earlier that magnitude is a fancy word for distance. Let me write that down again over here. Magnitude is the same as distance. And we're looking at geometry. Magnitude is the same as distance. So if you recall, right, distance is Pythagorean theorem, okay? So I'm looking at my triangle. A squared plus b squared equals c squared. What is the length of this vector? So the magnitude is 4 squared plus 2 squared, which is the square root of, this is 16 and this is 4, so the square root of 20. That's it. So the length of that vector is root 20. Anyone watching live, if you got a question, let me know. But, I mean, that's everything right there in a nutshell that we need to know about vectors. We need to know how to name them. We need to understand that they're directions. So don't overthink it, right? You can follow the arrow. You know the path of how to get from one point to the next. It's kind of everything there in a nutshell. So let's just take a look at another one. Kind of the same idea. It's not plotted for us, so let's go ahead and plot it. A is at negative 2, 4. So negative 2, 1, 2, 3, 4. And B is at 0, negative 1. So right there. And if we connect the two together, there is my vector. Yeah? Go back up a little bit. Yeah, what did we miss? I need more? Like the tippy top? If you're watching the replay right now, just speaking to the replay viewers, right? Since I'm interacting live here, you can skip ahead to when we get back down to the notes, right? You don't have to watch us interact. So there's our vector a to b. All right. So name the vector. Well, it's of course vector AB. Why not BA? Because we didn't start at B. We started at A. So AB. And in component form is this thing, right? That is our component form. And the coordinate form is when we do this, okay? So please know the difference between the two of those. The component form is this guy. So what do we do? Again, look at our directions. We went right 2 and down 1, 2, 3, 4, 5, and down 5. So I can immediately jump to my component form of 2, -5. And I can also say we added 2 to x, and we subtracted 5 from y. And again, I hope that makes a whole lot of sense, right? Because I mean, we literally have the two coordinates right here and right here. -2 plus 2 gives me 0. 4 minus 5 gives me -1. Look at that. Okay. One more thing with vectors, not to overkill us here, we're almost done with vectors, is to draw a vector, right? If I give you the vector, do you know what that looks like? So TQ, what is this saying? Left 6, down, up, because it's positive, up 3. So draw a vector that can, and just draw it anywhere, right? This right here does not tell you where it is, right? You realize that, hopefully. When you look at that, like, it just says left 6, up 3. Where does it go? It's not specific, okay? It doesn't tell you where it's at. It tells you how it moves. And that is the important part, because a vector is more like directions, right? A vector isn't just an object that you just set on the table. A vector is directions. It's a movement, okay? I know that's kind of a weird thought, but don't think of vector as a thing. Think of vector as directions. So left 6, 1, 2, 3, 4, 5, 6, and up 1, 2, 3. So I'd land right there. Left 6, up 3. 1, 2, 3, 4, 5, 6, and up 3. So it says to write the vector in coordinate form. So what do? We subtracted 6 from our x value, and we added 3 to our y value. To go left means to subtract. To go up means to add. What's up, Uzi? So what is the magnitude? Again, this is just a Pythagorean theorem problem. So the square root of a squared plus b squared, which is the square root of 9 plus 36, which is the square root of 45. And you could plug that into your calculator and get a decimal. I'm not going to bother with that. I'll let you do that on your own. Okay. So for the sake of time, I'm not trying to make this super long. Let's jump in. I think we get the point. At least I hope we get the point, and if not, we'll figure it out along the way. Let's take a look at the transformation called a translation. So a translation is a transformation along a vector such that the segment joining a point and its image has the same length as the vector and it's parallel to the blah 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 blah. That's a long sentence, right? That's the super formal definition. A translation basically means to shift an object. Take your cup, take your hydro that's sitting on the desk and slide it. I'm going to take the mic, right? I'm going to take the mic and slide it across the desk. You can probably hear that as I slide it. I'm not flipping it. I'm not spinning it and rotating it. I'm simply shifting it directly to the right or directly down or straight up or straight left. So the act of moving left to right and the act of moving up and down, that shifting, right? The orientation of the mic is still the same. It's still facing me, but it's just a little to the left or a little to the right or a little bit further back or a little bit, but the orientation is still the same. So translation is simply shifting. And we need directions, right? How much do I shift it? Well, that's what a vector tells you, right? A vector is directions. To represent a translation of a preimage in a function notation, we write, so there's this function notation again. What did we see before? We saw reflect, we saw stuff like this, right? That's what we saw. And what does that say? Reflect this point across this line. Okay, well, ignore that because we're not looking at reflection. What does this say? It says to capital T translate that point P along the vector V. That's what it says. So capital T stands for translate. What are we translating? An igloo? An iguana? An Eskimo? No, we're where did those words come from? We're not translating people or animals. We're translating the point P. Specifically, let me call it the preimage. We're translating this point P, the preimage. How would you like me to translate it? Well, follow the directions. And your end result is P prime. We would do this in class with some tracing paper, but we don't really have tracing paper. So we're gonna skip straight to the graphs. So, what do we have here? We have an image and a preimage. And it says what vector got us here, right? What vector shifted A to A prime? What? Let me do a different color so it stands out more. What vector shifted us from A to A prime? What vector shifted us from B to B prime? Well, it says name the vector. So how do we name it? Well, we use the starting point and the ending point and this the little thing. So that's easy. That's the name. What are the directions? You can probably already see the directions, right? You can already see the movement, hopefully, right? We went 1, 2, 3, 4, 5 to the right, and we went 1, 2, 3 down. Same thing for B as well, by the way, right? It's not like this is exclusive to A. We went 1, 2, 3, 4, 5 to the right, and 1, 2, 3 down. Everything got shifted. All right. This entire segment just got scooted to the right 5 and down 3. So in component form, which is what looks like that, component form, it went right 5, down 3. And in coordinate form, again, it's really not that different. We're just kind of writing it. We're writing it a little differently, but it says the same thing. It says add 5 to your x value and subtract 3 from your y value. We feel good about that? I think translations are the easiest, right? I think reflections are second easiest, and translation are the downright easiest to understand because it's literally just about counting. So if I told you, this is just some quick maths right here. What are each? Let's think about what these are saying in words, and then we'll just get to our answer super quick. So what are each of these saying in words, and then we'll just get to our answer. So it says to translate this point left 3 up 2. Translate this point up nothing, or left nothing, sorry, down 3. Translate this point right 7, down 12. That's all they'll say, right? We need to realize that we should be able to look at this and know immediately that this says left 3, up 2. If you can't see that, you need to go back up and re-listen to vectors, right? But these directions, positive and negative, left and right, up and down, positive and negative. So this is simply down 3, and this is right 7, down 12. So let's do the math on that. If I'm moving left 3, that means I'm subtracting 3. And if I'm moving up 2, that means I'm adding 2 to the y value. So 2 minus 3 is negative 1, and negative 4 plus 2 is negative 2. I'm not moving left or right, so I'm adding nothing. But I'm moving up 1, I'm moving down 3, so I'm subtracting 3. So negative 3, negative 2. And you could do a quick sketch on a graph, right? I mean, like, if a graph helps you, right? There's my point, negative 3, 1, left 3, up 1. And then if I move it down 3, 1, 2, 3, where am I going to land? I'm going to land at negative 3, 2, right? Right where I said I was, negative 2. So don't overthink it. And then the last one, if I'm moving right 7, I'm going to add 7. If I'm going down 12, I'm going to subtract 12. And I end up with negative 2, negative 17. So let's translate, aka shift a few more graphs, and then we're golden. So draw the image of the triangle under the translation negative 3, 2. So you should immediately look at that and go, oh, I'm moving left 3, up 2. So let's do it. Left 3, left 3, left 3. Each of those points is moving left 3 and then up 2, up 2, up 2. Do you need to draw that every time? Of course not. But I'm trying to create a visual for you. I want you to understand how each of these points are moving. Beautiful. So we moved them along the vector That moved us left 3. I was trying to get the arrow to click there. Left 3. Why isn't the arrow clicking? Left 3 and up 2. Well, that one worked. Whatever. What is this one telling us to do? This one's just straight up telling us to go right 4. Don't go up or down at all. So 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So here, here, and here are our new points. So our triangle looks like so. Why didn't you click into place? Beautiful. That's easy, right? Easy. Notice how it kind of looks like a 3-dimensional shape when you draw it out. Kind of neat. Not really a coincidence. I like these, and if you thought you were confident on all of them, these are the true test. If you understand these, you're golden. All right? So here we go. What is this telling us to do? It says to take our pre-image and reflect it across the line y equals -1. What up, Miles? We're almost going to start Algebra 2. Because you're in Algebra 2, right? So there's the line y equals -1, and we're going to reflect it. Remember, it's symmetrical. So if C is 2 above, well then C prime is 2 below. If B is 4 above, then B prime is 4 below. All right, so let's go ahead and plot those points. So C's up there, C prime's right there. 1, 2, 3, 4, 1, 2, 3, 4. There's B prime. And A is 1, 2, 3, 4, 5 above. So 1, 2, 3, 4, 5 below is A prime. So there's our first image. And then what do? We take this image, and now we're going to translate it, which means we're going to move it left 5, up 1. So let's do that. Left 1, 2, 3, 4, 5, up 1. Left 1, 2, 3, 4, 5, up 1. Left 1, 2, 3, 4, 5, up 1. So here, here, and here is our final image, which is A double prime, B double prime, oops, C's at the top. C double prime, B double prime. Those of you watching live with me, Geo folks, do we feel good about that? Because if you do, you're doing great. We have a question at all? So the last one's the other way around. What does it say to do first? It says to translate the triangle left 2, down 4. So let's do that. Left 2, down 4. Left 2, down 1, 2, 3, 4. There's C prime. Left 2, down 1, 2, 3. Oops. Left 2, down 1, 2, 3, 4. There's B prime. Left 2, down 1, 2, 3, 4. There's A prime. So there's our first image. Oh, you got a little bit of a delay there, eh, Emily? Well, ask a question to help alleviate Any confusion there? And then we're going to take that image that we just created and reflect it across the line x equals -2. I kind of grazed over the fact, I kind of just plotted this line like right away, which I'm sorry that I did that. I probably should have reminded us that, okay, the line y equals -1 is horizontal at -1. Okay, which is why I drew this horizontal line at -1. Now this guy, x equals -2, is vertical. So 1, 2, there's my line of reflection. And when you reflect something, everything's equidistant. And I'm trying not to draw too many lines, but it's kind of hard to show you what I'm doing unless I actually click on it, right? When I'm hovering, you can't see what I'm doing. So I actually have to draw on the page in order for you to see it. Whoops. So what I'm counting is, all right, C prime is 1, 2, 3 away. So on the other side, it's going to be 1, 2, 3 away. There's C double prime. B prime is 1, 2, 3 away from the line of reflection. So B double prime is going to be 1, 2, 3 away over here. Stuff now that I've already counted it. And then lastly, A prime is 1 away, so A double prime is 1 away on the other side. A double prime. And why is it the same? Because it's a reflection. It is symmetrical. That's what a reflection is. It's symmetrical. It's got to be the same on both sides. And there is our end result. Do you have any questions? Sorry, talking with my mouth full. Yay! Making an announcement for Algebra 2 that I'm about to go live for them. Do we have any follow-up questions? Any final thoughts? All right, then. Well, we're going to hang for just a few minutes till maybe a few Algebra 2 kids trickle in. Yep. That's how it always goes down. Classwork's always over the stream. Whoa! The Wahoo emote. Saw a slight spike in viewers on my end. Do we have some Algebra 2 people on here ready to go? Sir. Matt on another level. MJ on another level. Here we go. Miles rocking the Wahoo emote. So, well, I suppose I got to get the right notes open. Give me a sec. That's my bad. It's easy, but actually. All right. Yeah. Good to go. I thought that was kind of obvious, but I guess I'll tell you. You're good to go. All right. So, the quadratic formula. So, the quadratic formula is a formula that could be used on every single quadratic equation to get your two solutions. When when completing the square isn't an option, well, completing the square is always an option, but when it's a messy option, you might want to turn to something else. Well, you could try out my U method, right? I wish I had a name for it. I need to come up with a name for it. But my U method, you could try that one, right? And I keep putting that on the table as an option because that one always works, right? A lot of these methods always work, but sometimes they're not. They don't always come out that clean. Quadratic formula is another one of those options that always works, and I'd but sometimes it just doesn't come out as nicely, or it's time consuming, or yada 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 yada, right? But it's good to know all these methods. So without further ado, let's just take a look at it. The quadratic formula. The quadratic formula is this: negative b plus or minus the square root of b squared minus 4ac all over 2a. You may or may not have seen this before in your lifetime. That's the quadratic formula, and it finds you your two solutions because you add the square root to find one solution and you subtract the square root to find the other solution. So this is going to get us our two solutions. So It's highlighted here on the page, and I'm going to highlight the entire thing. The expression b squared minus 4ac under the radical sign is called the discriminant. It's called the discriminant. And it has a fancy word because the discriminant allows us to offhand see whether or not it allows us to know offhand what type of solutions that we have. We know that when we take the square root of a negative number, we get an imaginary solution. So, if the number if the expression under the square root, called the discriminant, results in a negative number, aka something less than 0, then we get imaginary solutions, because when you take the square root of negative, you get an I. That's pretty obvious. If the number under the square root ends up being something bigger than 0, well, then you're just going to get a real solution. And by real, I mean like normal, like regular numbers, no imaginary. And if on the off chance you get 0, well, there's only one solution, because adding 0 and subtracting 0 is the same thing. It doesn't make a difference. So, the first few questions just simply ask us to find the discriminant. So let's do that. So the discriminant is b squared minus 4ac. And when we look at this expression, we need to know what is a, what is b, and what is c. So let's see. A is 1, b is negative 3, and c is 5. I think we probably know that at this point. And so let's plug it in and see what we get. Negative 3 squared minus 4 times a times c. So I get 9 minus 20, which is negative 11. So the thing under the square root is negative. What does that mean? Well, that means we will have two imaginary solutions. We'd have a plus or minus I situation on our hands. Okay? Because when you take the square root of a negative number, boop, out pops an imaginary. Let's look at this one. A is 3, B is 1. There's a 1 there that we can't see. C is negative 2. So again, we're just only focusing on the discriminant part because we don't know what the final answer is, but at least we know what type of solution we have on our hands, okay? Which is nice information to know. So b squared minus 4ac, 1. So negative 4 times 3 is negative 12, and negative 12 times negative 2, bloop, out pops a positive 24 because the two negatives cancel out, and we get 25. So we have a positive solution, so we'd have two real solutions in the end. So let's just offhand on Desmos compare those two graphs real quick. X squared minus 3x plus 5. Because again, I think it's worth knowing, like, why do we care? Just to clarify. When you look at this graph, the one that had two imaginary solutions doesn't even cross the x-axis. Doesn't even cross the x-axis, which is why the solutions are imaginary. We can't see them. The one that had two real solutions, well, clearly it crosses because, well, the solutions are real. So the imaginary one doesn't cross at all. That's the context here. That's the situation. When it comes out as negative, it's imaginary. When it comes out as positive, it's real. Correct. Because this is the thing under the square root. If the thing under the square root is negative, well, that's when you get an Jeez. If the thing under the square root is negative, taking the square root of a negative number results in an imaginary. If the thing under the square root is positive, well, no big deal. The thing that we always still have to do, though, we always got to set it equal to 0, right? That's what we always do, right? I mean, we have to have the expression like so, because having the number on the other side makes it a little confusing. We need to know A, B, and C. C is not -9, it's +9, because everything's got to be on one side together. Then we can know what A, B, and C are. So move it over to the other side first. Then we can truly see what C is. So now when we do B squared minus 4AC, we get -12 squared minus 4 times 4 times 9, which is 144. And I already did this one ahead of time. Spoiler alert, 4 times 4 times 9 is 144. I had to look that up. I had to punch that in. And I get 0. So when you get 0, you have one real solution. And again, why is that? Because this is the number under the square root. What's the square root of 0? 0. So if I add 0 and if I subtract 0, that's not changing anything. I'm only going to have one solution. Again, we got to get everything on one side together, so I'm going to subtract that over. So now I can see that A is 5, B is -2, and C is 4. So B squared minus 4AC. B squared minus 4AC. So 4 minus 4 times 5 is 20. 20 times 4 is 80. So 4 minus 80 is -76. So once again, I'd have two imaginary solutions. Okay. So let's do it all the way out. Let's actually solve one of these guys. So we set it equal to 0 first. And we can see that A is 2, B is 1, and C is -5. And I already wrote this in standard form over there, so draw an arrow. Okay, there we go. There's my standard form, ax squared plus bx plus c. So when I go to plug it into the equation, I get, and let me write that down again because it's on the other page now, -b plus or minus the square root of b squared minus 4ac all over 2a. So in this problem, we get -1 plus or minus the square root of 1 squared minus 4 times a times c all over 2a. I plugged in all those numbers. Plop. And now we just very carefully do the math. And would my U method work on this? Yes. And if this looks daunting to you and you're like, I swear every time I do it with the U method that pans out just fine, or you know what, I don't mind completing the square, and yeah, sometimes I get weird fractions, but I'm okay with that. If that's your thoughts, then I'm really not trying to force you into a corner here with this quadratic equation. But if you do like it, or if this is something that you're interested in, right, this is another thing that works every time. So it's just something to try. So let's keep it going. So I get 4 times 2 is -8 because of the negative there. And -8 times -5 is 41. All over 2 times 2 is 4. Not 41. 4. I was jumping ahead in my brain. And then 1 plus 40 is 41, but I'll go ahead and write that as a separate step. So we have real solutions because the discriminant turned out to be positive 41. The number under the square root is the discriminant. And so, I mean, this is basically our solutions, right? And as a decimal, those two things equal... Let's plop it. We got negative 1 plus the square root of 41 divided by 4. And then copy that and paste. So you can see here, we've got 1.4 and negative 1.5. Or negative 1.9. I can't read. And there it is. We got our two solutions. I think the numbers pan out too nicely on this one. So I'm just going to make something up. I don't like how nicely the numbers pan out. So let's do one where when the numbers pan out nicely, great, whoop-de-doo. But, the numbers pan out nicely, you could have done it with completing the square too, right? If we have time, I'll do that problem. But I want to do it with gross numbers here. So negative 2x minus 8x is negative 10x. And then you also subtract the 4 over. You got to get it in that standard form first, right? You got to get it in that standard form first. And then you can see that A is 3, B is negative 10, and C is negative 4. So let's see what happens here. Again, that equation is negative b plus or minus the square root of b squared minus 4ac all over 2a, which is negative 10 plus or minus the square root of negative 10 squared minus 4ac. And this is where all over 2a. And like right here is where students like to screw up and think they can skip things, and they see the negative, but they forget that it says negative in the formula, so the two negatives are going to end up canceling, but they forget that, and that's why I write it all out like so. And then I start to cancel stuff out. So those two negatives are going to cancel. And then when you square the negative, that negative is going to cancel. And then these negatives are going to cancel. So we got plus 4 times 3 is 12. 12 times 4 is 48. All over 2 times 3 is 6. So I have 10 plus or minus the square root of 148 all over 6. And boom, there's my two solutions. And that's something I can plug into a calculator. Let's see what that one looks like. So 10 plus the square root of 148 divided by 6 and minus 148 divided by 6. So there's my two solutions. I got 3.7, or depending on how I tell you to round, this time I'll do hundredths. So I've got negative 0.36, and I have positive 3.69. There we go. This is easy, right? We can stop if we're done, if we feel good. We can do one more, or we can do two more, or we can do three more. How about I for grins, because I always like to bring it up. Compare it with my original method that I showed, because sometimes I just feel like that. I don't know, there's something about it that just works out nicely. And let's just do it to this one, right? Let's just do it to this one. But I'll do the quadratic formula first so I don't start confusing you with anything. What did I do first? Standard form. Gotta move the 4x over so that way you have ax squared plus bx plus c. Gotta have the three terms. And notice I take the time to put the 4 in the middle, right? It goes x squared, x, and then the constant. Okay? Trying to keep that order. So a is 3, b is 4, c is 10, and the equation is negative b plus or minus the square root of b squared minus 4ac all over 2a. So that turns into negative 4 plus or minus the square root of b squared minus 4ac all over 2a. So I've got negative 4 plus or minus the square root of 4 squared is 16. 4 times 3 is 12. 12 times 10 is 120. So minus 120 all over 6, which turns out to be negative 4 plus or minus the square root of 16 minus 120. Do it in your head, plug into a calculator, you get negative 104 all over 6. So, interestingly enough, we have ourselves our first imaginary answer. Which, spoiler alert, there aren't any imaginary answers on the classwork because it's like impossible to type into Canvas, so. But nonetheless, we get that, right? Because out pops an I, and we've got that. I'll leave that on the screen as I work over here. Let's see what happened over here. Remember, with my U method, I have to make a 1. So I immediately jump into fraction zone. And I know that immediately turns people off. So you might already be like, this method sucks for this one. But, you know, I'm inspired to do the whole thing, so I'm going to do it anyway. So b over 2 minus u times b over 2 plus u equals c. So in this case, that's 4/3 times a half is 4/6. So half of 4/3 is 4/6 minus u, 4/6 plus u equals c, which is 10. Then I multiply those together and I get 16 over 36 minus u squared equals 10. Ten-thirds. My bad. So then 16/36 plus 10/3 minus 10/3. I gotta move the 10/3 over and the u squared over, so minus 10/3 equals u squared. Yeah, I can already see that most kids are not gonna want to use this method. But like I said, I gotta finish it out. I multiply by 12 because 3 times 12 is 36. Now I have a common denominator. So 16 over 36 minus 120 over 36 equals negative 104 over 36 equals u squared. Take the square root. I end up with u equals I root 104 over 6. Boom. You see that? So 4/6. And remember, it's always the opposite, right? So negative 4/6 plus or minus I root 104 over 6. So it comes out the same. I can already tell that was just. You just spoke a whole different language, lol. Yeah. The U method on that particular problem is just not as ideal. Fractions, man. Love them or hate them, they don't go away. Do we want to see another one, or are we good? I can make up another one and not use the U method. This picture right here, by the way, is just demonstrating what I said earlier, is that when you have imaginary solutions, it's not gonna cross. When you have two solutions, or when you have your two real solutions, you're gonna see it cross, and when you have only one solution, it's just gonna touch once. So that's just like a physical representation of that. Okay, one more. Give me the numbers you want, or do I just make it up? Do you care? Or is there like a number? Is there like numbers that you're like, what if it does this? What if it does that? Or is it just random? I'll just make it up. Um, negative 7x squared plus 4x minus 8 equals, well, negative 7x squared minus 4x equals 12x plus 6. So what's the first thing we do? Get the standard form. So negative 7x squared. Subtract the 12x, you're going to get negative 16x. Subtract the 6, we're going to get negative 6. So we got a whole bunch of negatives. So A is negative 7, B is negative 16, C is negative 6. The equation is negative b plus or minus the square root of b squared minus 4ac all over 2a. So let's plug that in and see what happens. So negative 16 plus or minus the square root of b squared minus 4ac all over 2a. So our negative b, the negatives cancel out with each other, and we end up with a positive 16 all over 16 squared is 256. And then there's lots going on here with our negatives. So a negative times a negative gives me a positive. But then positive 28, which is the result, right? Negative 4 times negative 7. Oops. Positive 28 times negative 6 gives me another negative. So positive 28 times negative 6 is negative 168 all over negative 14. And again, I like to take it, I mean, you could break this up and go just like super step by step. So there's the 256 part. Then the next step would be to handle that. So what happens here? 256. You can do it super step by step. Negative 4 times negative 7. Well, that's positive 28, but we still got to multiply it by 6. Now we'll multiply it by 6. I was doing some of this, all at once, but I'm taking it super step by step because why not? So 28 times negative 6 is negative 168 all over negative 14. I'll go ahead and multiply that together finally. And then 16 plus or minus the square root of 256 minus 168 is 88 all over negative 114. And then from that right there, you could plug into a calculator. You could plug this all into a calculator to get your decimal, but in my personal experience, students do not know how to use a calculator. And they would punch this in incorrectly. Try punching that into a calculator, whether it's a Google calculator or Desmos. I'm not sure. I have full confidence. So I do a little bit of math here, and then we get this answer right here. This is the exact answer. And then your rounded answers come from your calculator. How do we feel now? Well, that's what I was showing here on Desmos, was that I was punching in the plus half of things and punching in the minus half of things to get my. It's not something that I can simultaneously punch in. So I punch in the plus side of things and the minus side of things to get my two answers. So I suppose to finish this out, what I had on my page was 16 plus the square root of 88 divided by negative 14. So there's that answer. And then I'm just going to go ahead and copy this. And I get negative or minus root 88. So my two solutions are actually both negative. So I end up with negative 1.81 and negative 0.47. And the questions on the classwork do indeed say to round to, I think every single one of them says round to the hundredths place. But it is a decimal answer, so none of this like x equals and x equals. You're just typing in the number. Do we call it there? Is that for us? Pretty short, sweet, and to the point. All right. Little Nat's all good. Uzi, you're good now, I take it? Feeling much better, you said? That Wahoo emote, though. Thank you. Miles is chilling. How about that? All right. I'll see you in class. Probably gonna play some Warzone.